Welcome everybody. Welcome Julia. And we'll give people a couple minutes to join the webinar, and then we'll get started. Yeah, thanks for joining us today.
Pleasure.
So how are things down in London? How's the weather out there?
It's nice. It's like springtime has almost started. At least after winter last week, we've got spring this week, so probably autumn next week. The usual.
Yeah, I hope we're not making some of our colleagues in the US jealous. I'm personally in California, so I'm in the small percentage of the country where things are actually quite comfortable. But yeah, talking to some people this morning in the Midwest, and they're all snowed in, and the power's coming on and off, and yeah, they seem to be some of the more fortunate ones. Should pass.
No, the UK is great for moderate weather. We don't get really hot summers, we don't get cold winters, so it's like eternal spring, autumn normally. But it was a cold winter. We had some snow, which is very unusual, actually.
Yeah, sure, lots of fog.
Yeah, yeah, transforms the city.
Okay, so I think I'll start with a few words of introduction, and then we'll get started. So my name is Moshe Safran. I head up the US activities of RSIP Vision, and our guest speaker today will be Professor Julia Schnabel of King's College London, about machine learning in medical imaging, from image acquisition to interpretation. Before we get started, a few words about our company for those of you who are new to the Bay Vision webinar, who have not heard us before. So we're an AI and computer vision solutions provider for medical devices and applications. We're a 50+ person company, a multidisciplinary team of AI engineers working together with medical experts and an innovation team. Our company's been around for over 25 years, and we work with mainly with the big US medical device companies. We create AI modules that get integrated and baked into their products for use in clinical and medical applications, mostly surgical and interventional use cases. Really, these issues of clinical robustness and image quality and artifacts, of which Julia is doing so much advanced and cutting-edge research, these issues are really part of our daily life of our team in our day-to-day work. Show you a few examples. This first example is our airway segmentation module. This has been used already in thousands of cases worldwide. It's integrated into one of our clients' products. And to get a robust airway segmentation system, it's not a trivial task. In a way, it's straightforward, but it's still not trivial. So the good news here is that chest CTs have relatively good availability. It's relatively easy to get a nice data set of thousands of CTs that's reflective of the variability of patients that are actually seen in the field. The image acquisition conditions are, a fairly controlled environment, and it's important to manage the process of building the AI solution here properly. So getting high-quality annotations, multiple cycles of development, failure analysis, understanding the edge cases correctly, properly rebalancing the data set, and retraining. And if you manage this process correctly, from our experience, you can get very good and very robust results. So it's not trivial, but in a way it's straightforward. Now, what happens if the data availability is less good? What if you're working with a modality such as ultrasound, which is highly operator dependent? This is an example. This module is currently undergoing integration in one of our clients' products. This is a TE ultrasound clip, and it's quite difficult to get, especially from this highly specialized specific device. It's quite difficult to get thousands and thousands of cases. You're working with something that will look more like hundreds or a few thousands of training data. That's one challenge. The second challenge is that the image quality is highly operator dependent. Each user is going to use it differently, and sometimes the input is not going to be suitable. You can't make it work in every situation. You can definitely not make it work if the proper view is not being acquired, or if the contrast and the information is just not there in the images. In this type of case, it's not enough to create a segmentation solution, create an automated measurement algorithm. You also need to supplement this with quality grading or automated quality grading module. So in this case, the user is going to be shown this quality bar showing when the image is the proper view, when it's high quality, and when it's low quality. And this way you add a little bit of control on your input, which can be very necessary for getting a good result. The third and final example I wanted to share, this module is currently under development in our company, and we expect to share more about it in a couple of months. This is a segmentation module for the knee joint, for bones, and for implants. And there are a few challenges here. So the first challenge is obviously doing a proper separation and segmentation of the implant, which is quite close to the bone. But a bigger challenge here is actually getting a robust and high quality segmentation of the bone in the presence of the metal artifacts that this implant is causing. And again, you can get a decent sized training data set, but smart data augmentation is quite necessary here from what we're finding as well, in order to generate enough instances of these artifacts so that the network really learns to perform robustly and is and you can really prove that it's going to generalize and perform correctly in these situations. Again, we in these webinars always try to bring people from the forefront of academic research, of industry research, who are really developing the cutting-edge technologies in these and other fields. And today our speaker is Professor Julia Schnabel. She's chair in computational imaging and head of research and impact at the School of Biomedical Engineering and Imaging Sciences at King College London, executive editor of Melba Journal. He's general chair at IMPI 2021 conference and will be general chair at MICAI 2024 in Marrakesh, very hopefully in person by then. Professor Schnabel has worked at a large range of areas over the last 20 years, including deformable image registration and complex motion modeling. In recent years, she's been developing novel machine learning and, of course, deep learning-based algorithms, including integrating model-based methods into deep learning settings. And in this talk, our speaker will present some of her approaches that operate from the imaging sensor all the way through the extraction of the end result and of clinically relevant measures, including realistic data augmentation and end-to-end solutions. The speaker will present examples from cardiac MRI and from fetal ultrasound, and will conclude with perspectives on the challenges that yet need to be overcome. Again, Julia, very honored and excited to have you here today, and looking forward to hearing your talk and your work. And without further ado, I will make you the presenter, and let's go.
All right. So can you see my screen?
Yes, I can see it. We see the whole desktop.
Okay, so that's fine. I'll just go. Just have to minimize things here. Oops. Oh, move away. Right. All right. Is that okay?
Perfect.
Okay, thank you very much for this really kind introduction and for this invitation. It's a huge pleasure for me to be here. I wish I could be there in person in California, not in London, but you see a little bit of London. I haven't seen London much in the last year, I must say, because I'm basically working from home these days, as most of you will be as well. So I want to talk a little bit about our research. It's not just my research, it's my research groups and my colleagues' research. And we're all very closely collaborating. We're actually in a teaching hospital, major teaching hospital, which is close to the London Eye. And we are actually, from my office, I would normally see Big Ben and the Houses of Parliament. So we are as central as you can be in London. These are my disclosures. I'd like to thank all the funding agencies which have supported our work. So in today's talk, I want to show a little bit some of the machine learning techniques which we've harnessed in medical imaging, because they've been really helpful in various applications such as image quality. We normally work with very well curated, high quality training data, but this is not what clinical reality is. So we have to do something about that. Also, machine learning is ubiquitous in the detection and characterization of image artifacts, organs, disease, and of course now in segmentation and more recently in registration tasks as well. So in our work, we apply machine learning to several things. One of the things I want to focus on today is artifact detection and artifact removal, so restoration of images using realistic data augmentation methods. We're looking a little bit into image fusion, which allows us for larger field of view imaging and ultrasound and improved organ detection and segmentation. And as Moshe already mentioned, we're working, of course, a lot, as the wider field is as well, on end-to-end solutions for all the above. Basically working directly from the imaging sensor to extracting some clinically useful measures. 2 applications will be dealt with. In the first half of this talk, I will focus on cardiac MRI, where we're looking mostly at image quality control to improve further downstream tasks. And the second half of the talk, I will spend a little bit of time on fetal ultrasound imaging. It's actually maternal ultrasound imaging, that's the same on detection and segmentation of the whole placenta. So I'm sure this doesn't need an introduction, but I just want to still say we're looking at the most common techniques in deep learning. So basically encoder or encoder-decoder networks such as UNet for segmentation, or encoders for classification or regression tasks, and maybe also some GAN style approaches. So it's nothing really novel what I'm talking about today. Basically, I want to focus on how we actually can use fairly simple setups like this for really, really helpful tasks. And sometimes simple is best, actually. So looking at this basic setup, an encoder network, we can actually classify images. We can say is good quality or is it poor quality in a supervised fashion. This is the same as classifying is there a dog or a cat in an image in computer vision. One application we looked at is scan planning. So basically looking at images like this, a 4-chamber view, which has to be acquired in cardiac MRI using first a 2-chamber view acquisition followed by a short axis acquisition from which the appropriate angle is selected, which has to then also exclude the aorta. And if you do that, you get a really beautiful 4-chamber view image. If you don't do that correctly, and that happens quite often, you get off-axis images. So you actually not only see the 4 chambers, but you also see the left ventricular outflow tract, the LVOT, which gives it like a 5-chamber look, which of course is wrong. And that poses difficulties in further downstream atrial analysis. So we can detect this. We can actually look at 2-chamber and 2D 4-chamber cardiac MRI, and we can find some good examples and some bad examples, train a very simple net style convolutional neural network, and decide on the output whether it's LVOT, whether it's 0 or whether it's 1. So basically it's good quality or the LVOT is present, or it's bad quality image. And we've done that with a fairly simple setup. So we looked at a balanced data set, basically using UK Biobank data. UK Biobank is a huge, really high quality controlled database, which is public. You need to apply for access permissions, but you have to give a project description, but then you can actually get access to data, to segmentations, to other things. Because it's such high quality data, we actually did not find many poor quality data sets, which is a bit of a conundrum if you want to actually design a method which could deal with poor quality data in a real hospital setting. But we lived with we worked with what we had. So we selected the 123 LVOT, so poor quality images, matched it with 123 good quality images. We have, of course, scener images, so we've got temporal frames. So we get 615 images for each class, and can also do tenfold cross-validation to boost the amount of data. And we've compared this with the standard machine learning methods at the time. This is from 2018 network, where we also looked at random forest and linear SVM and so on. And we also just applied CNNs to that without any augmentation, just with normal rotation translation kind of augmentation. And we actually got some really promising results. What we also looked at, if you look at data which has the LVOT present or a good quality image in comparison, you can actually look also at the LVOT, at the attention map of these images after passing images through the network. And the attention maps for these 2 cases look quite different. So the LVOT image actually shows directly where the aorta is present, a kind of a higher level of response, where the good quality attention map focuses more on the separation of the heart chamber. So this is just one example. That was quite promising at the time, because we thought we can actually see what the network sees and make it a little bit more interpretable and accessible for the radiologist. So moving a little bit further down, we actually acquire other poor quality images in the clinical setting. Patients, they move in the scanner, they can't hold their breath very well, and of course they've got cardiac problems. That's why they're being scanned in the first place. So the question is, can we turn a poor quality image, and rather than calling back in the patient and throwing away the image and saying you have to come again, you have to scan again, can we turn it into a good quality image using, again, a fairly simple encoder decoder architecture? So it's basically an image restoration problem. So here's a particular motion artifact shown on the right. The left, you see a good quality image, and the motion artifact image is basically like a motion blur. You see basically several cardiac phases at the same time. And this is because the way the images are acquired is that you do an ECG trigger and you acquire always across the cardiac cycle and fill the entire cardiac cycle up within a single breath hold. And you keep going until across several breath holds until you're done. So if something is wrong with this ECG trigger, you might actually acquire the case baseline of the MRI for the wrong cardiac cycle, part in the cardiac cycle. And that's a bit like seeing through the cardiac phases all at once. So again, UK Biobank is a really, really good database. I've got now 50,000, target is 100,000, I might have just reached it. I do even follow-up scanning now. At the time, we looked at 3,500 subjects, and we only found just over 100 subjects with this motion artifact, which could be arrhythmia, breathing, or this mistriggering, which I've just described. So again, super severe class imbalance problem. So we actually said, rather than just doing the normal data augmentation of translating and rotating our images, let's do something more realistic, because we know exactly where this motion problem occurs in case space. So just a brief primer on case space. So we've got different frames which are acquired. So we can look into the Fourier domain. And then we actually see the scan lines on the bottom right. So what could happen then if we actually start mixing these scan lines from different parts of the cardiac cycle, we get exactly this mistriggering artifact. So that actually helps us to look at good quality images, of which we have plenty in UK Biobank, and corrupt them. So we're very good in making images look bad, basically. But that's basically what data augmentation means in this case. So this is quite realistic. So we can, with that concept, take a good quality image and turn it into really a low quality image. And we can do it gradually. The more case baselines we mix, and with more time frames in the cardiac cycle, the worse the image starts to look. But these are actually realistic images, because this is exactly what is happening, which is quite nice. And in a way, it's the same as wriggling around a cat and doing this normal case-based augmentation, translation, rotation, but here we actually do it using the MR physics. Okay, the next step is to think about, okay, we are already in case space, so rather than transforming our image into the spatial domain and then operating on that, we know that the motion artifact occurs in case space, so can we actually learn the transformation and go from case space into the real domain at the same time? So there was this article by Zhu et al. In Nature 2018, where they actually did work on that. They did it in 2D, which suits us because we work on 2D cinecardiac images, and they actually learned basically the inverse Fourier transform. So that's quite nice. What they basically were looking for is looking at undersampled case space. So basically, case space where some lines are missing. Yeah, so we just acquire 70% or 50% of the case space to accelerate imaging. And then the output is a reconstructed high-resolution image, which looks much better than if you would just do zero filling and an inverse Fourier transform. So that's what the normal algorithm does. What we want to do, of course, is have a corrupted complex case space, which isn't undersampled, which is fully sampled, but it's corrupted because some case baselines are just wrong. So we can train a similar network. We actually do a little bit of an addition and add a little bit of a discriminator. We put in a corrupted complex case space, fully sampled, and as output we get an artifact corrected image. That was quite nice. We can actually see what's happening. We've got a synthetic corruption on the top. You don't see that in case space. It just still looks like a Fourier image. If you just did a reconstruction using inverse Fourier transform, you see image B. If you apply our method, you see actually it looks a bit blurry, but that's quite an interesting feature. And on the right, you see the original. Now the problem is it looks a bit blurry, our method here, but if you look carefully, you see that the Fourier reconstruction is actually wrong. It is actually doing exactly that motion blur. It is actually reconstructing the image at a slightly wrong cardiac phase because it did not correct for the corruption, whereas our method, which has learned the corruptions, actually gives a more faithful representation of the cardiac phase. So we can also look at real corruption. So this is an actual corrupted image. It's case space. The reconstruction, of course, is the same as the original in this case, and our proposed method. The next thing is to think about segmentation, because we not only want to reconstruct images, we want to do something useful with them. We want to calculate maybe ejection fraction or myocardial thickness or thinning or anything like that. So we can use a similar approach. We can use, again, like a unit star encoder-decoder architecture to do segmentation. There are plenty of methods there. We use the one via Benjai from Imperial College. And the problem is it works really nice on good quality images, as shown on the right, the original image with good segmentation. If we corrupt that image using our method, we actually get a corrupted segmentation. It actually just breaks because that network was trained on high quality images, so it can't do anything useful with corrupted images. But if we take that image and decorrupt it, so it's on the far right, our decorrupted image, which looks a bit blurry, you actually see we can reconstruct most of the segmentation, whereas the other methods in literature actually still fail on that. So here are just some numbers. Basically what we've also done is we looked at the mean squared error and the loss function combined with the SSIM, which is used in reconstruction, and that gave us those best results in the end. We compared it against just a normal case-based reconstruction and different methods in literature. So revisiting that is, of course, we know how the motion corruption happens, but could we actually remove those wrong case baselines rather than just being able to ignore them in the reconstruction? So this then turns the artifact correction problem into an image acceleration problem, because once we remove wrong case baselines, we are left with an undersampled case space. And this is exactly what methods like compressed sensing in traditional sense or these deep learning methods for image reconstruction have been trained on. They can actually look at an undersampling trajectory and compare that with a fully sampled acquisition and learn the reconstruction. This is done using a data consistency term in addition to the reconstruction term. Again, we can simulate that quite nicely because we actually can displace case baselines, then train a network to classify case baselines as either wrong or correct, and then get our undersampling trajectory as well and add it to a reconstruction network. So this is what we're doing here. So we have a fully sampled acquisition of which some case baselines are wrong. But we actually can detect the case baselines in the detection network. We've got our artifact image, which we put into our reconstruction network, and our detection network gives us the sampling trajectory, the data consistency term, which is fed into the reconstruction network, which gives us then in the end a fully high resolution motion corrected reconstruction. So here's just an overview of the whole thing. One nice thing which one can exploit in 2D scenic cardiac MRI is that you don't just use a single time frame, you actually have the whole scenic sequence. So actually there you can exploit the redundancy of the data, put into recurrent convolutional neural network, and then apply the data consistently on all time frames at the same time. So you actually reconstruct the whole senior series in one go. So it becomes almost a 3D reconstruction problem. Of course, it's different cardiac time frames in 2D. Our training objective is then just listed here. We've got a detection term and a reconstruction term in our loss function. Here are just some results. We have a good quality image, a corrupted image. We've got our case spaces. We looked here at 200 training data, 50 for validation, 50 for testing. And our proposed end-to-end method actually gave us the most favorable results. The bottom line in the table actually uses the proposed, uses the known mask. So rather than the detected mask, we actually, because we corrupted the image, we can actually apply also, instead of the detection network, the known mask of wrong case baselines. And we can only get slightly better through that, which is quite nice because it actually, this gives us the upper error bound. On the right-hand side, you see we can also apply this to an uncorrupted image, because even though we apply it to good quality images, do the corruption, for good quality images themselves, there could be some minor artifacts as well, which we don't know because they're inherent in the data acquisition. So there we don't have a proposed known mask, we just have our end-to-end solution. We get really good results using the standard measures. So we can actually just use this method generally for image reconstruction, whether it's on good or poor quality data. So yeah, just some results on the corrupted image reconstruction, the ground truth and the difference image. We compared against our previous automap-based GAN approach as well, and our new approach was better. Next step is to put in segmentation into the whole thing. So rather than just doing the artifact detection and reconstruction, we also can train on segmentation at the same time. So I'm not going to dwell on this. It just says tells you how modular this all is. We can actually put all these different tasks together. It's not a multitask network. It's more like really putting everything together, training at the same time. What we found here, and you can read it in our TMI paper there, is that the segmentation task actually helps the reconstruction task, not only the other way around, which is quite nice. These two work together quite nicely. And then finally, on cardiac imaging, we're also working on artifact rejection, so really just detecting good images, rejecting poor images, doing a full cycle segmentation, computing all the parameters, doing output quality control, and assess ventricular function, all in one big framework now. So the second part of the talk is now on fetal imaging, or rather placenta imaging. I wanted to show you, let's see whether this movie works, our setup. So we've got a fetal imaging project where we actually can try out things in real time, because ultrasound really lends itself to deep learning methods. It's a real-time imaging method. Deep learning at inference time is nearly real time as well. So while you scan, you can actually analyze the images directly. The nice thing here is that we have looked at solutions which would allow us to acquire better quality images already, because as Moshe said in his introduction, it's very operator dependent, how much pressure you put on, what probes you use, how you angulate the probe. It's hardly reproducible. So what we did here is to use a multiplex in our ultrasound system. So we can use up to 4 probes simultaneously. Simultaneously, not quite. It's dependent on the frame rate. So at every only 1 probe fires at a time. But you can actually join those, have several probes. We've done with up to 4 now. Our favorite model is 3 probes. We've done a 3D print of a multiple probe holder. You see it on the left, so you see it in action here by our sonographer, just really passing gently across the patient. It's a bit like a tummy massage. It's quite easy in handling. It's not too heavy, and so what you get there is actually multiple views acquired at almost the same time, which gives you a much larger field of view. So that's really neat. We also, of course, have 3D ultrasound, and we've got the full video streams as well. So it's a lot of data we're acquiring now. So here you see what happens if you want to image the placenta. Depending on the position of the placenta, you can acquire the whole placenta in one go, or you need to actually move around the probe a lot, or you can use our multiple probe setup, as you see on the bottom. So with 3 probes, and we can fuse those images. We've done several different techniques on what the best one is. And you can actually acquire the whole placenta in one go. So then we just trained, again, a simple UNet approach for segmentation. We've done manual placenta segmentations and trained networks, and we had different network setups. So we've actually looked at feeding in the individual views, training the CNN and on those, and then fusing the segmentation output. We used just the multi-view image, train the CNN, and to get one joint output. And we did like a mix of both, because we can feed in both these individual views and the fused view as well. So that was quite an interesting exercise. We had 127 3D ultrasound images from video streams from 30 patients. We used 2 probes or 3 probes. We had different numbers there, and you see kind of the placenta here shown in anterior and posterior positioning, and you see actually how difficult, how varied that data is. Also, placenta doesn't have a very easy shape. It looks really different for every patient, so it's really hard to train. So we train probably more on the texture, on the speckle and the features than on the shape. This is just a passing through the manual segmentation, in this case, of 2 patients. Okay. So here's a second trimester case with the posterior placenta, which you see here, single view and multiple view fused, and an anterior placenta, which is much more difficult to image because you only get a partial view in the multi-view image. It's exactly there where I think we can make a difference. So we've done, of course, comparisons with our segmentations and the manual segmentations, and our multi-view results generally were better. Our S2 was just training on multi-view images, not the individual images, but there we had just fewer images, fewer samples. So I think but still slightly better than just doing signal view segmentation. We also looked at MRI here because we do a lot of fetal MRI, which is its own big problem with this correction of motion. And we segmented the placenta in ultrasound and MRI for the same patients. Of course, there is a residual deformation problem, which we haven't started yet. So we've got more interest in volumetrics, because the size of the placenta, which really matters. When the placenta stops growing, that's the time that you have to probably get the baby out, otherwise the nutrition will go down and will be a small baby of low birth weight. And you actually see some really good correlation between our methods, the ground truth ultrasound and the manual MR segmentation here as well. And here's a fusion of the ultrasound with the MRI, which is probably quite hard to see. Baby is upside down, in case you wanted to see one eyeball. And here's just some animations, how this looks like, the segmentation and the whole baby space taken from the MRI. And you see in yellow the extracted placenta from ultrasound, and red from MRI. In just more recent work, we've also looked at the differences in position with the anterior and posterior position, which and you also see that the fetus is in the way sometimes, right? So there we looked at, can we actually classify where the placenta is? It's again like an image quality problem. So we've combined an image segmentation problem with an image classification problem, again using an encoder-decoder style architecture to actually first classify where the placenta is, and then feeding that knowledge into the segmentation network. So we have a multitask learning method, which basically looks at the encoder and decoder methods at the same time. And we just combine those two in a loss function. That's our latest work presented at the MICA workshop last autumn. So in terms of future directions, I'm really interested in image quality control detection for what's called active imaging. So we can take real-time decisions on which and how many data you need to acquire, or whether you need to reacquire more data. And doing also real-time image fusion and disease and organ detection. And basically, we are operating now along the entire imaging pipeline, from scanner right to clinical interpretation, which is a really exciting area to work in. I'd like to acknowledge all my fantastic researchers. This was the last time we got together physically as a whole group. It was Christmas dinner 2019, and I miss everyone, but it's basically Esther, Veronica, and Ilka and Bram who did most of the work. I mentioned their references a bit earlier. Mini plug, IPME is we just sent out notifications. We still hope to have a physical, at least hybrid conference on the sunny island of Bornholm. You're surely working on your MICA abstracts, which are due tomorrow. But MICA 24 really should be a safe bet. First time going to Africa, and I really hope to see many of you there. It will be absolutely fantastic. Moshe mentioned MELBA, our new free open access journal, which publishes also special issues from MELBA from middle last year and IDME this year. And we have pushing our first papers out, so please consider submitting to us. And I'd really like to thank RSIP Vision, Moshe, and also Ralph, who actually brought me on board several times for the computer vision news, for inviting me today. Thank you very much.
Thank you very much, Julia. And yeah, I'd like to encourage our audience to take this opportunity. If anybody would like to type in any questions for the speaker, now's your chance. Yeah, and thanks for the mini plug for us. I don't need to plug Computer Vision News again. And Ralph, he needs nobody else to plug him. Our next webinar will be in late March, fourth week of March. So we'll invite you guys to that. So please keep in touch. We can be reached on LinkedIn. You can reach me by email. And again, please feel free to type in any questions. Sorry, I didn't mention that at the beginning. Julia, I had one question actually about the first task you mentioned. Perhaps the answer was already there towards the end of your talk. So for the straight up image quality classification task, where high quality was no LVOT, 4-chamber view in the MRI slice, and the LVOT images were low quality, do you think it could have been helpful there also to do some kind of multitask learning, like if you had trained the network to segment the LVOT when present jointly with classification? Sort of more in general, when do you think doing that kind of thing is worthwhile and efficient, and when is it enough just to do sort of vanilla classification?
Yeah.
And that's it?
I think segmenting the LVOT is probably clinically not very interesting. You don't want it in the way when you want to look at your 4-chamber view, but you could combine it with a 4-chamber view segmentation, for example, and the reconstruction as well. And that actually might help the classification task as well. Ideally, what we would want to do is just maybe acquire just a few case baselines, detect already then whether the LVOT is present, feed that back to the scanner operator and readjust the angle.
Readjust, okay.
And basically almost learn the perfect angle to which acquire the images in the first place. So having a feedback loop in real time, I think that would be the way forward to avoid that problem.
Cool. Yeah. So rather than just trying to get the network to do the quality grading better by teaching it another task that might not be needed in itself, try to actually solve this problem at acquisition time and feed it back in time.
Yeah, absolutely. So basically, at operating time, while the patient is prepared in the scanner, basically get fast acquisition done, but also get good quality acquisition done. So learning basically scanning protocols, almost that would be the best thing. So having patient-specific angulation, whatever TR values, whatever you need for MRI to get optimal scanning done.
And updating that in real time based on what the machine is seeing.
Yeah, and we're not that far away from that. I think for undersampling, all these things already exist. Things like bias field correction you can do at scan time. So yeah.
Related question actually from Aditya. So how would the case-based artifact detection work for other 2D, 3D protocols such as MPRAGE or TSE?
Yeah, we haven't done that, so I wouldn't know. I would be curious and try it out. So this is a very specific artifact we've looked at, which was ECG mistriggering. So where we exactly know what's going on. But of course, you've got a whole range of artifacts, and that actually takes me back when we looked at respiratory motion models. And so you could actually probably simulate respiratory motion. It's a bit harder doing that in case space directly. You would probably do it in the spatial domain, go back to Fourier domain, which comes with its own thing because you not only then have the magnitude and not the phase images, so you don't have the true case space, but just the Fourier domain magnitude image. But you could think about what other artifacts are there that you could realistically simulate. That could be motion, generally breathing, periodic motion of the breathing that could be possible in case space. Patient movements, just translation, shifting around. Of course, we do that by normal augmentation, but there's no reason why you couldn't do it in case space directly, and detect it in case space directly. That would be the exciting thing.
Yeah, it's great how, despite the fact that the deep learning models themselves are sometimes so opaque, we can still use this domain knowledge to improve results. And yeah, that it's not like just an empirical or a black box effort. It's really using what we know about how the images are acquired and making that in is really helpful and useful here. We've got a much higher level question here from another member of the audience, but I'd like to share this. What are the top 2 books you would recommend for someone who wishes to update their knowledge of medical imaging with respect to AI engineering?
The top 2 books. I mean, one book I've recently read, which I really liked, was just, it's a bit further away from deep learning. It's called Deep Medicine by Eric Topol, which actually sets up why we want to do deep learning, why we want to relieve the radiologists from sitting all day around in a dark room, rather than talking to patients and actually taking diagnostic decisions. So that for me was a good setting to actually think about it. My good books, I mean, I don't have it on my desk right now, but there is the deep learning book by, gosh, my brain's gone blank. It's just called deep learning, I think. I'm happy to email that through later on. So that gives a fairly good general introduction. And you have to start back. If you're as old as me, which you're probably not in the audience, it's nothing new. Deep learning is not new. It's convolutional neural networks were invented in the early 1990s, late 1980s even. So actually I've worked on some number recognition when I studied computer science. So the main techniques are quite simple. It's very simple maths in the end. What really drives us now is we've got more data, we've got more annotations, we actually have more compute power. I think these are the 3 things which actually lifted us off about five years ago, maybe, where ImageNet came and all these other things. That's why I still like working with these really simple ones. I mean, I've shown Lynette actually from Yann LeCun, which was one of the first, convolutional neural networks, and it still works. That's the beauty of it. It's actually the learning curve for deep learning is not steep. You can actually start quite quickly.
Yeah. So some of the older model-based techniques are actually much more difficult to understand and much more challenging, in a way, deeper. But yeah, in the end, all this linear algebra is really performing very well just once we have the data and the compute. Yeah. Not a question, just a quick comment. I love your idea to train on bad images to be more clinically relevant. And yeah, I second that comment from Jordan. And yeah, as you showed in some of the examples, like we all want to get a lot of good data, but we also need to get a lot of bad data. And really, when we can't get it, to generate it ourselves, and that's really key for turning these solutions into really clinically relevant systems that are going to be working and going to take all that work off the shoulders of the radiologists, right? Because in the end, the problem today is not that radiologists don't have enough work because AI is doing everything. It's still, the problem is still the opposite, that they have so much work and so much routine work. And yeah, hopefully AI will be helpful in taking some of that work off of their hands and automating it.
Yeah, it should relieve them of the more mundane tasks, and they can focus on the really tricky cases, which actually your network might fail on, in fact, because there's some really rare hard conditions, for example, which really take specialist knowledge. What we're doing also is we're looking at different scanning systems, different field strengths. We're looking at older data from the same patient, because we've got access to hospital data from years back. So we have to deal with all these differences in image quality. For MRI, it's still fairly easy because MR physics helps us. Ultrasound, I think, is the ultimate challenge. Because quite often you don't have the raw data. You have only the B-mode data. You quite often only have the video stream or the screen snapshots from the video stream, which have been even hand labeled by the operator. And going there back historically is almost impossible. We're trying to do that as well, but it's a really big challenge. But just trying to help the operator while scanning, directing them to the right position, to the right scan plane. We're doing also scan plane detection and things like that. That's quite good. It's good for training the operator as well. Basically telling them you're getting closer, move the probe that direction, and you're nearly there. So it's actually quite a neat teaching tool in the end.
Yes. Okay, so thanks again, Julia, very much. And again, we'll be in touch, and hope to see everybody again next month at our next talk. Thank you, and have a nice day.
Thank you very much.
Bye-bye.
Bye.